Welcome to the Makeup for the Atomic Emission Spectroscopy Lab. I just want to take a couple minutes and review the process of electron excitation, since that's exactly what you're going to be seeing during the course of this lab. So we know that electrons are spinning around on the outside of the nucleus. So the first thing that's going to happen is that they're going to become excited. So some form of energy is going to strike my electron, and that can be many different forms of energy, whether it be light or electricity or heat. Some form of energy is gobbled up by that little electron, and he uses that energy, starts to spin faster and faster, and starts to escape the gravity of the nucleus and moves up from the ground state, which is where he started, into something called the excited state, a higher level orbit around the nucleus that is spinning much, much faster and a little bit further away. Now this is temporary, he can't stay there. So eventually the electron starts to lose that energy and falls back from the excited state back down to the ground state, and in the process emits a photon or light. Now what's interesting is that for more complicated atoms that would have more and more rings, we have to consider every style of ring jump, every place where they could start and end, as a potential place where you could have excitation, or in other words, different colors of light could potentially be possible. Because remember, the color is equivalent to the amount of energy, and it's only going to take a very specific amount of energy to jump from ring to ring. So I've drawn in here all of the different arrows for possible transitions or jumps that the electron can make, and every single one of those jumps should emit its own color of photon. Now what's weird is when we go to flame test, we only see one color, because as these different colors of photons hit our eye is so sophisticated that it doesn't want to confuse our poor little Neanderthal brains and merges all of those colors down to one color so that we can more easily and simply interpret the world. And unfortunately, that's really going to work not in our favor during the course of this experiment. We need to be able to see all of these different colors. So we're going to need an aid, an assistive device to try and get us through making these observations. We're going to use instead something that looks like this. This is called spectra paper. It's essentially a piece of prism paper, and what that allows us to do is to spread the light back out so that we can actually see the colors that are present. So we're going to put this paper between our eye and our light source on the outside. We call that light source an emission tube. It's really just a fancy light bulb. And that light bulb is going to be streaming electricity into an atomic sample for us so that we can be able to see it. And that prism paper should then spread the light back out so that we can record our observations. Just wanted to make sure that you had a little bit more of a sophisticated look at what this is going to look like. You can see the purple gas discharge tube or an emission tube glowing in this picture. This one has it focusing the light through a slit. We are not going to be having the ability to do that during the lab. And then the light passes through a prism. We're using prismatic paper, and then it actually displays an image on the back screen. Now, after every single discharge tube, I'm going to show you not only what we actually see in lab, but then also what the official spectrum it actually looks like. And that's what that image is actually called. You can see the one for hydrogen up at the top showing 4 distinct lines, not something that we would call a continuous spectrum, which would be every single color of the rainbow without stopping. This has very distinct areas of blackness on the inside of it, showing only 4 distinct colors. So here we go. Our first discharge tube is hydrogen. You can see this really beautiful purplish color with your naked eye. Again, that's your eye taking all of those different colors that should be coming out of this atom and interpreting it only as one. Now I hold up the spectra paper in front of the tube, and this is what you can kind of see. Now this is a distorted image. It can't be perfect, and you can see that the image actually also repeats. But if you'll notice the image to the far left side, you can actually see 4 very bright lines in front of kind of some smudgy rainbow color in front of it. which matches up really well with the official spectrum of hydrogen, which actually does have 4 recognizable lines. There are 3 that are in that blue purpley kind of color and 1 very distinct red line. Let's go back to that original observation so you can kind of see how that can be reinterpreted and reimagined as the official spectrum. Now this would have been taken in absolute perfect conditions with a perfectly polished prism in a perfectly dark room to be able to get a crisp image like this. And that unfortunately is not necessarily what our classroom conditions are. Also, don't forget that this drawing that we can actually make of the light that's coming out of the hydrogen sample passed through the prism is called an emission spectrum. So this is what you should be drawing on your observation paper, the emission spectrum, starting from red and going all the way through the violet tones for hydrogen. So let's take a look at a couple more elements. Here is helium. And you can see that it's a similar but not quite the same color as what we see with our naked eye with the hydrogen. This one has a little bit more yellow in it. So I wonder if that's actually going to show up when we put the spectra paper in front of it. So here is what I see when I put the spectra paper in front of it. A couple different things. Yes, we do see a little bit more yellow in that tone, which I think is kind of neat. And more notably, I see more lines of color, more bands of color than what we would see with the hydrogen. And remember that helium has 2 electrons to rattle around, whereas hydrogen only has 1. So maybe that makes sense that with more electrons, we should see more colors. Here is the official helium spectrum. Let's take a look at some more elements. Here is neon. This is what's actually used in neon lights. So again, here's neon with your naked eye. You can kind of see that it's that nice red color. And we do use these a lot in neon signs because they do glow so brightly. I put the C spectra paper in front of it, and this is what we're going to end up seeing. Now this image is really hard to see, so I wanted to make sure that I captured it so you could see that the image was repeating. I'm taking a look at the image all the way over to the left-hand side, and you can see there's a great number of bands of color, but they're in this like red and orange tone. There's a couple different yellow ones. I think it might be valuable to see the actual official spectrum. And you're going to kind of laugh when you see the official spectrum because you're going to say, oh my gosh, where are all those colors coming from? So here's the actual official spectrum. I'm kind of blown away with how many green and blue tones there are in this one because in the C spectra version of it, I don't see those at all. And I think it's just because the red and the orange and the yellow are so bright that they're overwhelming the remainder of the spectrum, that we are just not able to see it with our eyes in our lab. But that's the official spectrum of neon. Now think about that. You have neon now. It has a whole full shell extra electrons than the helium does. And look at what that does to the overall spectral image. Look at how complicated that is and how many different electron jumps. Because remember, every single one of those little bands of color coordinates with an electron jump. Let's keep going with our observations. Here is argon. You can see both the tube with your naked eye and the C spectra paper on this lovely page here. Look at the complexity of all of those different colors. Don't misinterpret this. Like when you see the big fat red band, our eyes aren't sophisticated enough to see all of the different tiny lines that are actually in there. It's just joining it together as one big fat line. That doesn't actually exist in these type of spectrum. So here's the official spectra of argon. Look at all of those lines. That's crazy. A couple other ones that are interesting. Here's krypton. Krypton has this beautiful kind of purpley, bluey tone to it when you see it with your naked eye. I'm going to skip over the C spectra paper image because it's that crazy hard to interpret and just give you the official version. Here's the official version. Tons of lines, and you can see most of them are over in that blue zone, which makes sense that that's more what we're going to see with our naked eye. Here's xenon. We're just marching down the noble gases at this point. So now xenon has a full shell extra electron. Naked eye color, we're seeing that kind of beautiful blue color. Here it is through C spectra paper. I just wanted to show you how the image is actually changing. This time it actually looks like a continuous rainbow, but I urge you to remember that it's really not a continuous rainbow. This is made of so many individual little lines that our pathetic eyes can't see the differences and the spaces between them. So let me show you the official spectrum. There's the official spectrum of xenon. Look at all of the lines, all of that complexity. So many electrons jumping from so many different possible locations. It was a lot. Now some other ones just kind of interest, and you're going to need to observe these for some questions I'm going to ask you later. Here is oxygen. Now oxygen is very difficult to see. It didn't want to glow very brightly, but there is a light, I would almost want to say a violet color to it. Hold it up to the C spectra paper, and this is what I see. Here's the official spectrum for oxygen. Now, oxygen is way smaller than, say, like xenon or krypton. And take a look at how that affected the number of bands of color. Now, even more interesting, here is nitrogen, ridiculously bright. And when I hold the C spectra paper in front of it, I get these really beautiful bright yellow bands. And then, of course, some other colors kind of mixed in with it. Hard to interpret because of that brightness. So here's the official spectrum. Looks similar to oxygen, but I think that the colors are more dispersed between red, orange, yellow, green, blue, purple. Another interesting one. Here is mercury. Very bright, very blue. In front of the C spectra paper. What I think is kind of interesting about this image is I see red, orange, yellow, green, blue, and purple. Every single one of the colors from the rainbow. And I think you'll hopefully see that when we see the official spectrum. You can kind of see there's at least one big band from every single one of the major representative colors. And why is this important? Well, do you remember light bulbs that look like this, those twisty light bulbs? Well, the material that's actually on the inside of that is mercury. And the reason that we put mercury in there and then exposed it to electricity is that it would go through electron excitation and give us photons or light, hence why it's really great for a choice of a light bulb. The reason that we chose that was because it mimics sunlight, because it has red and orange and yellow and green and blue and purple fairly evenly distributed. Here's another one of interest. This is water vapor. Water vapor kind of has this purpley violet undertone. I know this image looks more red, but it's more purpley violet. It's not bright, but it's still there. So now I want you to think about lightning. Now, lightning is electrons moving or electricity moving through the atmosphere. That could potentially spur some electron excitation. Now, I want you also to remember that the atmosphere is made of 78% nitrogen, 21% oxygen, and 1% other gases. So when you're seeing lightning, why does lightning look so bright? You can probably use your previous observations to now explain why. Or why, when we see lightning during a storm, when it's actively raining, why do we see it being purple in tone? Because oftentimes it can be interpreted as purple. I'm going to ask you yet another question, which you're going to respond to in your lab notebook. Would lightning on other planets look the same as it does here on Earth?